Hello, this is Jack Jackson. This is the third of a series of videos reviewing some Unit 1 problems from Survey of Calculus. This particular one, we're talking about some shortcut formulas for finding derivatives and a couple of related problems to that. And before we get started with that, let's review a few formulas from algebra. So remember that if you have a times n over b times n and n is not 0, then that equals a over b. That's sort of our basic equivalence property for fractions. So one of the things that you can do that's useful in some cases is you can multiply the top and bottom of a fraction by the same non-zero number. Sometimes that can be useful. Another thing that's going to show up is sometimes we'll have to take a fraction and subtract 1. So remember, in general, when you're adding or subtracting fractions, you need to get a common denominator so that you're adding up or subtracting pieces of the same size. So what we do here is we rewrite 1 as b divided by b, b over b. We keep the same denominator of b and then just subtract the numerators. So a over b minus 1 turns out to be a minus b over b. Then we have our negative property of exponents. B to the negative n is 1 over b to the n. So that negative power flips this over to the denominator. B to the n over m, if n over m is reduced, is b to the n, and then take the m root of that. So the numerator power is the power that's under here. The denominator power is the root. So in particular, like say, for example, 1 over 3 power would be the cube root. And of course, if we put these two properties together, if we have b to the minus n over m, then that would be, well, 1 over b to the n over m, so that would be 1 over the mth root of b to the n. So those are some useful algebra formulas and from basic algebra and arithmetic that we might want to use. Now we also have some shortcut formulas for derivatives. In these particular examples, f, g, u, and v are going to be functions of x, and b and n will be constants. Okay, so first of all, we have the sum rule that says the derivative of f of x plus g of x is the derivative of the f plus the derivative of g. So if basically the last thing that you do in this thing you're taking the derivative of is addition, you can break it into two derivative problems. And of course, hopefully one of both of those problems are a little bit easier than the original. We also have a constant multiple rule that says the derivative of a constant times a function. That constant can be brought out front of the derivative sign. So it's a constant times the derivative of the function. Or we could write it this way. Now the product rule is a little more complicated. The product the derivative of a product, so if the last thing is multiplication here, you take the first factor times the derivative of the second plus the second factor times the derivative of the first. The quotient rule, derivative of f of x over g of x, is the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. G of x times f prime of x minus f of x times g prime of x over g of x squared. The chain rule is used when you have a substitution. And so you let u be some function of x, some collection of the x stuff and operations. You let that be u and substitute for that, so then you have a function of u. So the derivative of f of u is just f prime evaluated at u times the derivative of the u with respect to x. Now, notice I've incorporated the chain rule in some of these rules down here. There are really only just 3 or 4 or 5 things that we know how to find the derivative of. The derivative of a constant is 0. The derivative of a constant times x is just that constant. The derivative of u to the n is n times u to the n minus 1 times the derivative of the u with respect to x. That's where u is the variable and n is the constant. So that's a variable base constant exponent. Now notice this one's opposite of constant base variable exponent. Derivative of b to the u is natural log of b times b to the u times the derivative of the u. And of course, if b is e, then the natural log of e is 1. So the derivative of e to the u is e to the u times derivative of u with respect to x. And the derivative of the natural log of absolute value of u is 1 over u times du over dx. And the derivative of ln of u without the absolute value is also 1 over u times du over dx, but it's only defined when u is positive. And so those are the basic formulas that will get us through any of the problems that we're likely to encounter in survey of calculus. Okay, now let us do a few problems where they're going to, as part of the steps at least, we'll be finding a derivative formula. So for example, let's do this application here. The average worldwide crude oil prices in dollars per barrel during February, March, and April of 2006 can be modeled by the function P of t equals 0.12 t squared minus 1.6 t plus 59.5, where t is the number of weeks after January 1, 2006. Use the model to find the instantaneous rate of change in crude oil prices at the end of the 11th week of the year. Be sure to include the appropriate units. Well, if we have the function here, remember instantaneous rate of change means derivative. So P prime of t is the derivative of that polynomial, and these are pretty easy to do, right? You just take the derivative of each piece. So the 2, use the power rule here, 2 times the coefficient, 2 times 0.12 is 0.24, and then subtract 1 from the power, it goes down to 1. Anytime you have a linear function like this, it's just negative 1.6, or if you want to think the power rule, it works. 1 times negative 1.6 is that, and this goes down to 0 power, t to the 0 is 1, so there's that, and the derivative of that constant term is 0. So there's the derivative, and then we just evaluated 11 by taking 0.24 times 11 minus 1.6, and we get 1.04. So at the end of the 11th week, at t equals 11, at the end of the 11th week, t equals 11, and the instantaneous rate of change in crude oil prices is $1.04 per barrel per week. So it's going up at about $1, a little over $1 a barrel each week, right there. Of course, we can also find this with the graphing calculator by just doing a numerical derivative, and especially if all we want is a decimal approximation, it will work that out. This is the older operating system on the T84, the Inspire, and the newer operating system on the 84 look like this, kind of like that. Try another one. Given the function f of x equals 8x cubed plus 24x squared minus 48x plus 7, find all the points on the graph where the tangent line is horizontal. What else do we know about these points? Well, the tangent line is going to be horizontal when the tangent line has a slope of 0. The slope of the tangent line is the derivative, so what we need to do is find the derivative set equal to 0. So once again, this is just a polynomial, so it's not too hard. We just follow this simple procedure. 3 times 8 is 24. Subtract 1 from the power makes it 2. 2 times 24 is 48. Subtract 1 from the power, it's 1. 1 times negative 48 is negative 48. That's x to 0, so that goes away. Derivative of 7 is derivative constant is 0, so that goes away. So notice when you take the derivative of a polynomial, it goes down 1 in degree. Now we want to set the derivative equal to 0, so we would take that formula, set equal to 0, and solve. Now in this case, I could divide both sides by 24, and so I do that, and it works out nicely. Whole numbers here, and of course it still didn't mess our 0 up there. However, at this point, if we want to find an exact answer, we're solving that quadratic equation, and to get an exact answer, we're probably going to need to use the quadratic formula. So, hopefully you remember that. It's the x equals the opposite of b over twice a, plus or minus the square root of b squared minus 4 times a times c, also over twice a. So this all cancels down to just negative 1 for that part. And this is 2 squared is 4. Negative 4 times 1 times negative 2 is positive 8. 8 plus 4 is 12. 12 is 2 squared times 3, so the square root and the square cancel here, leaving 2. The square root of 3 is still underneath. This 2 and this 2 cancel, so we get negative 1 plus or minus the square root of 3. So one answer is negative 1 minus the square root of 3 for x, and the other one is negative 1 plus the square root of 3 for x. We can take those and plug those back into the original formula, which is what I've done right here. and work this out to get the corresponding y. Now I left out quite a few steps here because squaring this out we need to like do FOIL here, and then we want to square this out and then multiply by another -1 to minus the square root of 3, and then distribute all these things, combine like terms, and when the dust settles, this is what you end up with. And then that is the y coordinate when this is the x coordinate up here. So the x coordinate is -1 minus the square root of 3, and the y coordinate is 71 plus 48 square root of 3, or approximately -2.73, 154. And that one turns out to be a local maximum. And then the one with the -1 plus the square root of 3 turns out to be 71 minus 48 square root of 3 for the corresponding y. And so that point, which is approximately 0.73, -12.1, that turns out to be a local maximum. How do I know that which one's a maximum minimum? Now, there's a couple different ways we could know that. When the derivative is 0, those are things where we might have a maximum or minimum. But we know they're max or min, if the second derivative is not 0. And so the second derivative is pretty easy to figure out here. 2 times 24 is 48, and that goes down to x to the first power. Derivative of this linear part is 48, derivative of that constant 0, so which is 48 times x minus 1. So notice anything less than -1 is going to be a negative derivative, second derivative, and anything greater than -1 is going to give us a positive second derivative. So this is -1 minus something, so that's less than -1. So this is going to give a negative number. So that means the graph, the original graph, the graph of f, is concave down, so there's a local maximum there. And similarly, if you take -1 plus the square root of 3 and plug in here, that's to the right of -1, so you see you get a positive second derivative. So the graph of f is concave up, but it's also stationary, so that makes it a local minimum. Or you could just graph the thing and tell that, oh yeah, there's a maximum here and a minimum here. So the one that's -1 minus something is the minimum, and the -1 plus something is the -1 minus something is the maximum. -1 plus something is the minimum there. And in fact, if we just want to find those places, that's going to be the same places where we have horizontal tangent line. If we just need a decimal approximation, or as a check of what we've already done, we can do a calc minimum for this minimum here, or calc maximum there. And if you notice, those decimal approximations for that point for that minimum maximum agree with the decimal approximations that I had up here. So if you just need the decimal approximations, of course, we can do it that way. All right, now we have a series of some just derivative problems where we want to find the derivative. So we'll practice doing our rules. So this one here is the derivative of x to the fourth times e to the x. So notice that if you were to plug in an x here, this is, by the way, this is the key to deciding which rule to apply first. Pretend you're evaluating the function, like we plug in a certain number for x and work it out. We would raise e to the x power, we'd take x to the fourth power, and then we would multiply. What was that last step? That last step was multiply, so we use the multiply rule, or in other words, the product rule. Now you need to memorize the product rule. In the product rule, it says take the first factor times the derivative of the second factor, plus the second times the derivative of the first. So that's x to the fourth times the derivative of e to the x, plus e to the x times the derivative of x to the fourth. And then we just do these separately. The derivative of e to the x is e to the x. The derivative of x to the fourth is 4x cubed. Now there's the answer, but we want to clean it up a bit. Typically we like to have it factored. If you notice, these both have an e to the x, so we can factor that out using distributive property or common factor factoring. And they both have at least an x cubed, so we can factor out e to the x and x cubed, and what's left here is just an x, and what's left over here then is just 4. So we get e to the x times x cubed plus 4. Of course, you could distribute that back out, and you'll get exactly this. How can we check our answer? You can check your answer to any derivative problem like as follows. Put in the original problem in y1, which you see I've done here. In y2, put the numerical derivative of y1. It may look like this, or it may look like Leibniz notation, d over dx of y1, such that x equals x. Okay, and then put your answer down here, e to the x times e to or times x cubed times x plus 4, and the tables for y2 and y3 should match, or at least it should at least approximately match. You might want to turn off y1 then, and sure enough, they do match here. So I may leave the rest of the checks. I've done a couple of the checks here, but then I ask you to do the rest yourself. Okay, so the next one, P of t equals 3t plus 1 over 2t minus 1. The last thing you would do here is divide the two things. So we use the division rule, the quotient rule. So the quotient rule says we have the derivative of higher over ho is ho d high minus high d ho over ho ho, or high over low, low minus ho, high, it's low times the derivative of the high minus the high times the derivative of the low over the low square. So the bottom is here, the derivative of the top minus the top times the derivative of the bottom of the bottom square. So the derivative of the 3t plus 1 is just 3, derivative of 2t minus 1 is just 2. Now we have the answer, but we're going to do some algebra to clean it up. We're going to distribute the 3 here to give me 6t minus 3, distribute the actually negative 2 here to get negative 6t minus 2. And it turns out when you combine like terms, the 6t's cancel. Negative 3 plus negative 2 is negative 5. And so there is the answer there. By the way, notice since the bottom is squared, it's always positive or 0. If the bottom is 0, the denominator is 0, the whole fraction is undefined. But otherwise, the bottom is positive and the numerator is always negative. So the second derivative, where it's defined at least, is always a negative value, which means the original function should be concave down everywhere it's defined. Once again, we can check by putting the original function in y1, leave y2 set up as a numerical derivative. If it were me for calculus class, I would just set it up like that and leave it all semester, and then turn it on or off as needed. Put your answer in y3. The tables for y2 and y3 match. Now when I say they match, y2 is actually symmetric difference quotient, an approximate derivative. The actual derivative is in y3. If you put your cursor on these values over here, you will see more decimal places, and there may be some difference way out in the decimal places, but they should agree to many decimal places. Let's do another one. If y equals u squared over 3u squared minus 2u plus 1, what's dy over du? Again, that's just what's the derivative. So this is another quotient rule problem. So that's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom square. Derivative of u squared is 2u. Derivative of this part is 6u minus 2. Distribute the 2u, I get 6u cubed minus 4u squared plus 2u. Distribute the minus u squared, I get minus 6u cubed minus plus 2u squared. Combine like terms, the u cubes go away. Negative 4u squared plus 2u squared is negative 2u squared. And then I got a 2u. I'm going to factor a negative 2u out of the numerator, leaving me a u minus 1. The denominator doesn't factor, so we'll leave it like that. And again, here's your check over here. By the way, notice these do check here. 5e negative 7 means 5 times 10 to the negative 7. That's 0.6 zeros and then whatever they have. So a 5. So that is practically 0. So to many, many places, these two answers are agreeing. All right, here's another quotient rule problem. What's the slope of the curve to the curve y equals x over x squared plus 1 when x equals 6? So the slope of the curve at a particular point is the slope of the tangent line is the derivative. So we just want to find the derivative again. So again, it's the quotient rule. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom square. Derivative of x is 1. Derivative of x squared plus 1 is 2x. Distribute, we get x squared plus 1 minus 2x squared. X squared minus 2x squared is negative x squared. We still have plus 1. We still got to have our x squared plus 1 in the denominator. X squared plus 1 squared. And then, well, that's the answer, but I could, if I wanted to, factor out a negative 1, leave me x squared minus 1, which basically factors as x plus 1 times x minus 1. So there's a factored version for this problem in the end. Now, that's just the formula for the derivative. The slope of this curve when x equals 6 is a specific value on that, which is take that formula and plug in 6. 6 plus 1 is 5. 6 minus 1 is 5. 6 plus 1 is 7. 7 times 5 is 35, and that minus makes it negative 35. 6 squared is 36 plus 1 is 37. 37 squared is 1,369. So if you divide that out, you get approximately negative 0.025566, etc. All right, what is the equation of the tangent line to this curve when x equals 6? Well, we have the slope of the tangent line. We need to find a point on the curve. Okay, so when x equals 6, y is 6 over 6 squared plus 1. That's 6/37. So now we have a point, x equals 6, y equals 6/37, and we have a slope, negative 35 over 1369. So in general, the point slope form of a line is y equals m times x minus x1 plus y1, where x1, y1 is a point